Got it. Right. Share screen. There we go. All right. Ready?
Hello, everyone, and welcome to the August meeting of the Delaware Valley Amateur Astronomers. We're delighted you're all here tonight, and we know it's pretty nice outside. So thanks for prioritizing this meeting for your attention. So the very first, we have a great presentation today, but the very first thing on our agenda is going to make an award to the winner of our youth awards. So I'm going to call Al Lamperti up. Al is the originator of this program.
This year we had 3 submissions for the DVA Youth Award. And the first place is Daniel Adibi. He's going to be giving you a short talk on his project called Differentiating Characteristics in Exoplanet Host Stars. So Dan, as you're making your way up here, we want to give you a certificate, a little check. You have a year's subscription to the DVAA. And if you see Dan leave after his talk, don't worry, he's going up to Reading because he's taking his SATs tomorrow. So he's only going into the 11th grade. So we can hopefully see him 2 more years.
When in doubt, guess C.
Here you go. Thank you. Here's the check. Good. Hold it up. Here you go.
Just one more.
Very good.
Congratulations.
Thanks. Good luck.
So now Daniel is going to share with us his research that won the award. And I understand this research has now been accepted into a journal, the Journal of Emerging Investigators, right? And it's in the publication pipeline. So that's cool. All right. Gotta find the card.
Here.
Good. Let's get that in your pocket.
All right. Everything good with the system? Okay.
We're good.
All right. Hi, everyone. My name is Daniel Adibi. I am a rising junior in high school, and I'm going to present to you today the project that I submitted for the DVAA Youth Awards, Differentiating Characteristics in Exoplanet Host Stars. Before I continue, I just want to thank all of you for your time, for listening to my presentation, for DVAA for offering the Youth Awards program, and for just being an amazing group. I'm really lucky to be a part of DVAA, so thank you for that. So yeah, let's get into the project. So I completed this project not this summer, but the summer before, right out of my freshman year of high school. I did it at Penn under the guidance of Penn professor Bhuvnesh Jain and now Cambridge graduate student Sarah Kane. And basically, I'll get into more details in a second, but I'm basically looking at what characteristics in host stars differs them from other stars in the galaxy. So let's see if this. Okay. So I'll just get into some quick background on a little bit of exoplanets and kind of where exoplanet science is right now. I suspect a lot of people here will already know a lot about this, but just in case, I'll just go through it really quickly. So basically, an exoplanet is any planet that orbits a star other than the sun. So that means it's a planet that is outside of our own solar system. To date, we've discovered just over 5,500 exoplanets, And we found many different types. There are terrestrial exoplanets, which are, rocky planets like the Earth that have a hard surface. There are gas and ice giants like Jupiter and Neptune that are made of primarily gas. Some orbit very close to their stars, some orbit very away. It's overall just a very diverse group of planets that we've discovered so far. The two main surveys that are discovering these exoplanets are Kepler and TESS. Kepler actually is no longer operating. It retired in 2018, but TESS is continuing to discover thousands of exoplanet candidates to this day. In terms of actual detection methods to detect these exoplanets, there are 5 main ones. I'm only going to go over the first 2 in detail. The other 3 aren't that important to my project. But basically, the main 2 that almost all exoplanets have been discovered with are transit photometry and radial velocity. So on the right, you can see some animations for how this works. Up on the top right here, you can see how transit photometry works. It basically works by monitoring a star for a long period of time and monitoring how brightness changes in a star. The hope is that if the star has an exoplanet, it will pass in the line of sight between that star and us and cause a little dip in brightness. And if we measure these dips in brightness for a star for a long period of time, if we see a periodic dip in brightness, we can conclude that there's an exoplanet there. And you can kind of see the animation there for how it works. It doesn't work for all exoplanets because not all exoplanets cross the line of sight between that star and Earth. It only works for some. But most of the exoplanets that we've been discovered have been found through that method just because of how convincing the evidence is once you do find that kind of transit. The second method is radial velocity. You can see a diagram of that at the bottom right. But basically, that relies on the fact that a star does not remain completely still when an exoplanet orbits it. In fact, what happens is both the star and the exoplanet orbit around their center of mass. Now, the star is so much more massive than the exoplanet that oftentimes that center of mass will be inside the star itself. But even then, it causes the star to wobble as it orbits. And this wobbling means that at times the star is moving away from us, and at times the star is moving towards us. And so that will create a respective Doppler shift, and we can detect that as periodic blue shifts and red shifts in host stars. And that will give us the insight. Okay, so now let's get into what exactly my study is. So I knew I kind of wanted to do something with exoplanets, and I was reading about, different exoplanet publications. I became pretty interested in the properties of the host stars themselves. What makes them suitable for exoplanet development? Why are they suitable? And what I found is that there hasn't yet been a comprehensive study that looks into which properties exactly differ and are important for host stars compared to stars that aren't host stars. And that's not to say that there hasn't been research in this. There's lots of research into what properties are important for host stars, but almost all of this research comes in the form of simulations, trying to simulate how different properties affect exoplanets. But we haven't actually had anything that kind of like overall, based on observed data so far, looks at which properties are the most important, just from what we've seen. And so I hypothesized that if I were to do this, I would be able to observe significant differences just from the 5,500 exoplanets that we have discovered. So I divided my experiment into 2 main parts. The first part was comparing host stars to the general stellar population. So basically just you pick a random star in the Milky Way, what's it going to look like compared to the actual host stars and their properties. The second part of the experiment was looking at different host star, what I call subpopulations, that are basically divided by the kind of exoplanet that a host star hosts. So let's say that like a host star, you could compare a host star that hosts a gas giant with one that hosts a terrestrial planet and see the difference between the two and what differs in terms of like stellar properties. You can see here, I have a list of surveys that I used. I used European Space Agency's Gaia, Chinese Society of Academics, LAMOST, NASA's TESS, and the NASA Exoplanet Archive, which isn't a survey by itself, but it's basically a really helpful database that has information about all discovered exoplanets so far. Okay, so now I want to talk a little bit about the methodology of my experiment. So the three main categories that I use to compare the different star groups that I just talked about are stellar classification, which isn't a great name, but it basically just refers to the evolutionary stage of a star, metallicity, which is how metal rich a star is, and kinematics, which is basically where a star is in the Milky Way. For all of these measurements, I used Gaia data, except for metallicity, where I used the most. That was just because Gaia specializes in getting a large amount of data for a lot of stars. I think it's like on the order of billions. But it's very good at providing kinematic and information on like parallax and visual magnitude. But it doesn't specialize in high resolution spectra, which is what you need for metallicity. So that's why I use the most, which is more focused on getting those like high fidelity spectra. And then really quick, just a clarification point with kinematics. Basically, when I say where a star lies in the Milky Way, I don't mean the exact position of where it is. I mean where it is in a general sense. And you can see on the right is a diagram of kind of generally what that is for a galaxy. There are three main parts of any galaxy. There's the bulge, that's basically the center of the galaxy. There's the galactic disk, which runs around it. And there's the halo, which runs above and below it, kind of all over the place. So what I mean basically is, does the star lie in the halo? Does the star lie in the disk? Or does the star lie in the bulge? And you're able to determine that based on the velocities of the stars relative to the center of the galaxy, which I'll get into more detail later. Okay. So now just to get into a little bit more detail on how exactly I collected the data. For the first part of my experiment, where I'm looking at comparing host stars to the general stellar population, I had three groups of stars that I used for my analysis. The first was just a random sample of stars in Gaia. It's a random sample of 1 million stars, and it's basically just representative of what the average star in the Milky Way would look like. The second group is test targets. That's just stars from the survey test that discovered a lot of the exoplanets that we know. And the third is host stars, just all known host stars so far. So comparing the random sample with the host stars would essentially tell us what differs between host stars and the general population. It basically tells us which characteristics are unique to host stars. But the problem is, this is incomplete, because let's say the surveys that are surveying host stars only look at main sequence stars. I'll explain what a main sequence star is in a second, but just for now, let's just say a survey only looks at main sequence stars. All of the host stars that you discover are going to be main sequence stars because that survey is only looking for them. There could be ones that are not main sequence stars, but you're not sure. So that's why you also have to include this group of test targets, so we can see if there's bias in the selection. And if there's too much bias, then we can't conclude anything intrinsic to the host stars. Then the second part of the experiment, where I'm comparing host star subpopulations, you can see right here, this is the table that has all of the classifications of exoplanets that I would use to characterize the stars. The labels kind of make sense. I just want to go over them really quickly so that if you see them later, you know what you're looking at. But basically, Jupiters are, some of the largest exoplanets we know, equivalent to like our Jupiter. We have Neptunes, and those are either classified as hot or cold, depending on how far away they are from the star. So a hot planet would be close, a cold planet would be far away. And then after that, we have ultra short period planets, which are abbreviated as USPs. Those are just very small planets that have very, very low orbital periods. And then we have super Earths, just terrestrial planets bigger than Earth. And then small terrestrials, which are terrestrial planets that are smaller than Earth. And then to kind of show how I divided host stars into these categories, because it could be a little bit confusing, I made a little animation. So let's say a star has a small terrestrial exoplanet. You can see it's small and it's close to it, so it fit under that category. I would then add that star to the small terrestrial host star category. HS just stands for host star. So those are just host stars that have small terrestrial planets. If a star has a cold Jupiter, for example, it would go in the cold Jupiter host star category. If a star has both, I would add it to a separate category that has stars with more than one planet, just so that we don't have overlap. Okay, and then a little bit more into the methodology before I get into the results, how I exactly compared these stellar characteristics. I used a variety of diagrams and statistical tests. These are the main three diagrams that I used. They're called HR diagrams, metallicity distribution function histograms, and tumor diagrams. And so I'm just going to get into a little detail about what they are. The HR diagram, which you see right here, that gives you very valuable information on a star's evolutionary stage. Now, what I mean by evolutionary stage is where a star is in its life cycle. A star will go through a lot of, it'll typically start off as like kind of an average sized star that's burning hydrogen into helium. Then eventually when it runs out of that hydrogen fuel, it will swell up into a giant or supergiant. And so you can tell what stage a star is in based on this graph. So on the x-axis, it's kind of hard to see, but you basically have the color of the star or the temperature of the surface of the star. And on the y-axis, you have absolute magnitude, which can be derived to give you luminosity. So it's basically a measure of how much light that star is giving. You can see this kind of main diagonal, that's called the main sequence branch. Those are all stars that are just fusing hydrogen into helium in like the main portion of their lives. Then you see the giant and the supergiant branch. They kind of branch off from the main sequence. Those occur when the star runs out of hydrogen fuel and begins to swell at the end of its life. So what I do is I would use that diagram to kind of visually inspect differences between star population. Then we have metallicity distribution functions. They're pretty simple. They're just, each star has a metallicity, which is an indication of how metal rich a star is. And basically it's just a histogram of that for a certain star population. So judging, you can like base it off of how frequent certain metallicities are. You can make conclusions about how metal rich that population will be. And then I'll get into a tumor diagram in a second because they're kind of more complicated. But before I do, I just want to go over the statistical tests that I also use. So beyond using kind of the standard like mean, standard deviation, median, I also used a variety of like more advanced statistical tests. The three ones that I used are KS tests, Anderson-Darling tests, and t-tests. And basically all three of those tests are looking at what the probability of two distributions being the same are. So essentially, they all kind of operate in different ways. Like a t-test will look at the mean and standard deviation, where KS and Anderson-Darling tests will look at something called a cumulative histogram. But either way, all of the tests will output something called a probability value or a p-value, and that gives you the probability that two distributions are the same. So let's say you had two metallicity distribution functions that look the exact same. Like they literally were the exact same distribution, you get a p-value of 1. If they were completely different, you get a p-value of 0. And a p-value cutoff of 0.05 is enough to rule out that the distributions are the same. That basically means that you're 95% confident that the distributions are not the same. And that I would use to determine whether differences in a distribution are significant or not. Okay, now just a little bit more detail into like scientific terms that are associated with my project. You can see effective surface temperature is not too complicated. It's just the temperature of a star's surface. That's what you see on the x-axis in the HR diagram, just measured in Kelvin like normal. Absolute magnitude is just how bright a star is from a certain distance away. It's like 10 parsecs. And you can use that to derive luminosity, which is essentially how much electromagnetic radiation a star will give off. Metallicity, I mentioned, is a measure of how metal rich a star is. The exact equation that defines it is here. You can use different elements to measure it. In my case, I'm using iron and hydrogen. And essentially, it's just a way of measuring the iron to hydrogen ratio compared to the sun. So if you have a metallicity value of 0, that means that the ratio of that star's iron to hydrogen is the exact same as the sun's ratio. If you have a metallicity value of 1, that means that that star has 10 times more iron compared to its hydrogen than the sun does. And then finally, probably the trickiest scientific terms here, but we have the kinematic velocities. These are sometimes called U, V, and W, which I just think makes it a little bit confusing. I think we're kind of used to, X, Y, and Z planes. But basically these are all just different velocities that a star has that will tell us information about where it lies in the Milky Way. So this diagram right here, this is showing Vy, which is also known as tangential velocity. And basically it's just how fast it moves around the Milky Way. So you can see you have a circular orbit here. That would be equivalent to the center of the Milky Way. That's the star. As it's going around the Milky Way, that would be the tangential velocity of it. And then we also have Vx and Vz, which don't have specific names, but they basically tell you how fast a star, how fast a star is moving away from its position in the galactic disk. So you can see Vz is right here and Vx is right here. So if both of those values were 0, it would just move completely flat relative to the galactic center, just kind of orbiting it like that. But if they increase in value, you start to get more deviation from the galactic disk, kind of something like this. And so what you can do is you can take the vector sum of those two velocities and take the magnitude of it, and that will give you the speed at which it's moving away from the galactic plane. Now, why do we care about this? Well, these can give us a good idea of where a star lies in the galaxy. So if you have a star that's in the disk, it would have a Vy value that's very close to the average, which is about 220 kilometers per second. And it would have very low Vx and Vz values because it's kind of just staying in the plane going around the star. But if you have a star that's in the halo, which is in that part that's all around it, you would have very, very high Vz and Vx values because it's kind of moving, not with the galactic plane. So in a tumor diagram, you have the tangential velocity on the x-axis, and you have the sum that I talked about earlier of kind of how the star deviates from the galactic disk on the y-axis. And basically, stars that are closer to the bulge or the disk will follow a tighter distribution and be close to the center, whereas stars that are in the halo will be more spread out and will show greater variation in velocity. And you can use that to figure out where a star lies in the Milky Way. Oh, sorry, one more term. There's also the total kinematic velocity. That's just kind of all of the velocities summed up together. It basically provides a way to quantify what's in the tumor diagram. But instead of being a graph, it's kind of a single value, which makes it easier if you want to use it for distributions. Basically, just a higher value, you're more likely to be in the halo. Smaller value, you're more likely to be in the disk or the bulge. So now let's get on to the actual results of my experiment. So I'm first going to present the results for the first part, which is comparing host stars to the general galactic stellar population. And then I'll get on to the part where I compare the subpopulations of stars based on the planet hosted. So I first started off with HR diagrams for the host stars compared to the general population. You can see here on the left, we have the HR diagram for the random sample of stars in the Milky Way. Here we have the HR diagram for host stars, and here we have the HR diagram for test targets. So just straight up, just looking at it from the start, we can see that the two distributions between host stars and the general population are very, very different, which indicates that there probably is a difference between host stars and the general population in the Milky Way. But we also have to note that TESS follows a very similar distribution to the host stars, which indicates that while it could be very likely that host stars have a very different distribution compared to the general stellar population, we can't rule out the possibility that it's following this distribution because of the survey. So essentially, the main difference that we're seeing is that host stars are orbiting fewer giant stars. But we can't conclude if that's actually intrinsic to exoplanets because the survey that was discovering them, TESS, also doesn't survey many giant stars. And we can see this with the t-test. We can see when we're just comparing the absolute magnitude of the stars, we can see it's very different for these two graphs, but then 0.059, which means it's similar for these two because it's not less than 0.05. So we couldn't conclude anything necessarily here. However, with metallicities, we had more luck. You can see on the right, we have the metallicity distribution functions and the histograms, and you can see that all three distributions look pretty different. And what that basically means is, so first of all, we have, you can see kind of the beige one in the background, that's the distribution for host stars. The Gaussian looking blue one is the distribution for the random sample. We can see that those are very different. So that means that there is a possibility that host stars are intrinsically more metal rich. The green one shows the test targets. So it clearly looks different from both distributions, which means that there is bias in tests. But the important thing is, when you compare it to the host star distribution, which is right here, it has a p-value of less than 0.05, which means it is significantly different and not fully responsible for the metallicity that we see there. So basically, the conclusion from this is that host stars are intrinsically more metal rich than the general galactic population. And while there is bias in tests, it does survey more metal rich stars. It's not enough to rule out the possibility. So we can safely conclude that host stars are generally more metal rich. Then onto kinematics. You can see here I have the tumor diagram for the three star groups again. We have the random sample, the host stars, and the test targets. And again, as before, as with the HR diagrams, we can see that the host stars are very different from the general population, but they do look pretty similar to tests. So again, we can't really conclude definitively that host stars follow a different distribution. And when we ran KS tests on the total kinematic velocity, we couldn't conclude any results from it. But if you do look at the percentage of stars in the halo, you can see that test targets had about 0.27% of stars in the halo, while host stars had about 0.082% in the halo. So there is a difference there. It wasn't enough for us to conclude that host stars definitely follow different distributions in terms of kinematics, but it is enough to suggest that the possibility is there. Okay, so now on to the second part of my experiment where I'm looking at host star subpopulations based on the type of planet hosted. We can see here, I went back to the HR diagrams for this. It is definitely a lot to take in. There are like 8 different graphs to look at. But the general trend is that distributions of stars had more dim stars when the orbital period and planet size decreased. That's kind of a lot to process. Basically, what that means is, as you're looking at planets that are closer to their star and are smaller, you start to see more stars that are dim. And this is evident if you look at, it's kind of hard to see, but if you look at, for example, cold Neptune, the distribution of that, those are very big planets that are very far away from the stars. If you compare that to the ultra short period planets, you can see that it gets kind of cut off here. You don't have any stars larger than a certain brightness. And the reason for that could be intrinsic to host stars. So you kind of see that you start to get more dim stars when you have planets that are closer to the star and smaller. But it could also be due to limitations in our detection techniques. And the reason for that is that exoplanets around larger stars are harder to see. That seems kind of counterintuitive because you think, oh, a larger star, there's more signal there. But the reason why is that a transit in front of a large star would have less of an effect than it would for a small star because you're not losing as much brightness relative to the total brightness of the star. And for radial velocity, because the star is more massive, you see less of a wobble. So it's actually harder to find exoplanets that are around large stars. And that could explain why we don't see any large stars for these kinds of planets. These planets are extremely small. And when you combine a small planet with a massive star, it might just simply not be possible to detect exoplanets in this region here, which could explain the trend also. So as with the HR diagrams before, while there are trends here, we can't actually be sure if those trends are intrinsic to host stars or if they're a result of detection techniques. In this case, it does most likely look like it is a result of detection technique limitations because the patterns fit very well. So we weren't able to conclude anything here. Again, with metallicities, this is a lot to process. It's basically a corner plot of each subpopulation compared with each other. It's not too important for the conclusions, but I just wanted to include that in the presentation. But this is what's more important. You can see here the statistical features for the metallicity distributions for each subpopulation. So you can see kind of a lot to process, but I'll just sum it up for you. The trend is that metallicity increases as planet size increases and as orbital period decreases. So again, if you look at large planets like hot Jupiters, they have pretty high metallicity, it's close to zero. But if we look at super Earths, which are much smaller and a little further away, they have like a much smaller metallicity. And the reason for this that I suspect, I'm not 100% sure this is why, but I believe it's because as you have like more as you have a more metal rich star, you have more metals that are exoplanets can use to develop. And as a result, if you have more metals, those exoplanets can accumulate more material and grow bigger, which is probably why we see more Jupiter-sized and Neptune-sized planets around metal-rich stars. And the thing about this is that we actually can conclude that this is intrinsic to host stars, because we saw negligible bias with tests when we were looking at the first part of the experiment, and metallicity doesn't have any effect on detection techniques. So this was probably it was a really interesting find to see that and to conclude that that actually is a property of host stars, and we kind of have now a definitive idea of how metallicity affects exoplanet development across stars. And then finally, the last result of my study is kinematics for host star subpopulations. Again, we have the tumor diagrams to the right. I apologize for the size of it. I was trying to fit everything onto the slide, and I couldn't really do it. It's really hard to see. It's not too important, but what's more important is, again, these distribution values right here. What we ended up finding is that it follows a similar trend to metallicity, which is that as planet size and orbital radius increase, the value of the total kinematic velocity decreases. With metallicity, we saw that as planet size increased, we saw a larger metallicity. And now we're seeing that if planet size increased, we're seeing a smaller value of the total kinematic velocity, which means that you're more likely to find stars in the disk if they have larger exoplanets. And at first, this may seem a little confusing, like why would where the star lies in the Milky Way have any effect on the exoplanet development around that star? It kind of seems counterintuitive, but the piece that puts it together is that stars that are closer to the disk and to the galactic bulge are generally more metal rich than stars in the halo. So I can't prove this, but my theory is that this trend in kinematics is just an extension of the trend in metallicity. Basically, as we have larger planets and planets that are closer to their star, we get more metal-rich stars, which means that we need more metal-rich stars in order to foster development for those planets. And we can only really find that once we're inside the disk or the bulge, which is why we're observing a trend in kinematics, when in reality, kinematics probably doesn't really matter for exoplanet development. Okay, so then conclusions and takeaways from the experiment. The HR, kind of the evolution, looking at the evolutionary stage of stars and looking at the kinematics of stars, revealed some potential trends, but due to bias in tests and due to detection technique limitations, we can't conclude if those are necessarily intrinsic to host stars or just a result of some other factor. However, on the other hand, we had very good results with metallicity, where we found strong evidence for differences, both between host stars as a whole and different host star subpopulations. And what we hope that this study can do is to essentially serve as a reference for other studies. So if another study is wondering what the general trend is, they can look to our study to see what it is, because we have done like a comprehensive analysis using all the data that's been available for us. In terms of recommendations for further research, I suggest analyzing Kepler data too, instead of just test data, to see if there's bias in that as well. It's possible that tests couldn't be a completely accurate representation of the survey bias that we see, and to also continue performing this analysis as we get more data and more exoplanets are discovered. And in terms of uses, it can be used to test planetary formation models. So if we're looking at, for example, how does metallicity affect exoplanet development? You could use that question to verify that a planet formation model is correct and make sure it follows the same trend that we observed. And we also foresee this as being used in surveys to determine which stars can be more hospitable. So for example, TESS is trying to maximize the chance that we'll find an exoplanet around a particular host star. After seeing such convincing evidence in metallicity, it could be used to further, make that requirement of metallicity even stronger so that it can maximize its chance of discovering exoplanets. That's it for my talk. Thank you all for your time and for listening to me.
Wow, that was just excellent, and I love the way you put it all in context
Thanks.
and explained why you were doing what you were doing. Do you have time for one or two questions?
Yeah, if anybody has questions, you can ask.
How did you hear about the Journal of Emerging Investigators?
How did I hear about it?
Yeah.
After I worked on my project, I knew I wanted to do something with it because I found some pretty interesting results and I wanted to share it. So I just kind of looked up the best, journals for like high school projects out there, and I found the Journal of Emerging Investigators. Yeah.
So did you have to do anything differently in your process to accommodate binary star systems that might host an
Yeah.
exoplanet? And if so, what was it?
Yeah, I'll go back to the slide. I didn't mention that in my presentation for the sake of time, but you can see here where I had like all the categories for exoplanets. Basically what I did was I just removed all the binary stars from it because I didn't want to. If you have binary stars, it's very different from just having a single star, and it's kind of hard to draw conclusions because it's just like such a different system. So I just decided to focus on single star systems for this study. Yeah. Oh yeah.
Yeah, this was a really fascinating presentation.
Thank you.
I'm a social scientist by trade, so I kind of think things through like an econometric lens when approaching like research methodology. And I know that's not necessarily the norm in the natural sciences, but I was thinking that potentially a zero inflated model could be useful here to get at some of the potential bias that might be caused by undetected stars with exoplanets and ending up in your just kind of general data. And so I was wondering if when you were going through this project, you thought of any alternative modeling specifications to get at these questions.
So I'm not like really familiar with the zero inflation model. Is that just to kind of like simulate what would happen if there wasn't bias? Or?
No, so what it does is it's almost like a logistic regression.
Okay.
But it takes cases that look very similar to the positive cases and says that that might be an excess zero, meaning a zero where it actually should be a one. And so you could potentially remove those cases from the sample to get at a better comparison between stars with exoplanets and stars without exoplanets.
Okay. I didn't think about that, but that's definitely an interesting suggestion. Yeah, that could be, I guess, one of the suggestions for future research or something. Yeah, that's a good point. Any other questions?
Take one more.
Okay.
I saw that you had, I didn't see references to the fact that metallicity, high metallicity does favor planet formation. What was the early references to this presentation?
Sorry, you just so you didn't see any references like supporting that fact, or
Corroborate what you put.
oh, that corroborated. Yeah. There's nothing that has looked at like done what I did where they look at stars, but the core accretion model of planetary formation, I looked at references of that which like simulated data, and it does seem to corroborate the results that I've had. So I did have some references.
Cool. Okay, thank you so much. We're not quite done with you yet. Did you put the other presentation? So we're delighted tonight to have a special guest with us. Chuck Allen, who's the president-elect of the Astronomical League, is here with us tonight. Actually, where did he? Oh, he's over there. Yes, so I wanted to invite him up because Daniel won a second award from the Astronomical League. Let me just welcome you.
That's not the award.
Okay.
Yes, can you darken?
Could you put the lights down? Thanks, Brian.
As vice president, we run all of our Horkheimer Awards for the Astronomical League, as well as the National Young Astronomer Award. And Daniel here, who I've not had a chance to meet in person, so I'll do that now, participated in 3 of those awards. This picture earned him second place. I thought it would get first personally, but I wasn't one of the judges in the astrophoto competition. It's the best photo I have ever seen. And if you see it on a computer monitor, it's even better to show the warping of M31 caused by M32 and M110. It's absolutely visible in this image. It's an overall view of the picture. You can see the left side kind of raised in comparison with the plane for the middle and the right side of the image here. An extraordinary effort and one of the best I've seen. Daniel also, as I'm sure you know, since he's a member here, is a tremendous resource for outreach. He taught students, I believe, in Libya and Afghanistan through online programs. In addition to that, I think that was through Astronomy for Equity program. In addition to that, of course, he started his own high school astronomy club, which we love to see because we need young people in the hobby, as we all know. Also, I think, began a series of programs taking astronomy into middle schools in the Philadelphia area. Tremendous service that he's performing from an educational standpoint. He was also one of the 10 submissions we had for the National Young Astronomer Award this year. And I can tell you that he was one of 4 that Dr. Keelkoff, or 5 actually, of the projects, that one of our judges said were equivalent to the work being done by research assistants at the graduate level. And his was one of them. And that's in 10th grade that he submitted this. So I hope he will continue to participate in the program. Our winner 2 years ago finished 6th, 3rd, and then 1st. In 3 successive projects. Just an extraordinary person. And since the subject here was metallicity, I'm going to give you a little sample from the collection here.
Oh,
This is a cubic inch of tungsten,
thank you.
which happens to have in it 1.03 septillion atoms. That is more atoms than there are stars in the entire observable universe, to a radius of 46 billion light years. So thank you very much and congratulations.
Thank you so.
Thank you.
Thank you so much, Daniel. Thanks for sharing your evening with us, and good luck on the SAT.
Thank you.
Jen, do you want to get a quick picture with that,
Oh, yeah.
with the lights on?
Yeah.
Okay, one more. Got it.
Thank you.
Thank
All
you.
right, thank you so much again.
Thank you.
Really appreciate
Yeah,
it.
thanks for the opportunity.
Take care.
Thank you.
Don't walk out with the microphone.
Oh, yeah.
Take the awards back.
And you probably want your check here.
Oh, yeah. All right, let's leave it here.
All righty.
All right.
Yes. Okay, we'll go back to. I wanted to invite Chuck to say a little bit about the Astronomical League just in the context of, if the Astronomical League, for those of you who don't know, is our parent organization that DVAA belongs to. And Chuck, if you want to be over here, that they'll see you on the YouTube video.
Sure.
Okay.
Okay. Just face this.
Do you want the left ear there, Mike, or this one?
This one.
Okay.
This will be fine. First of all,
I turned it on.
okay. First of all, I came here just to be at this meeting because I've seen pictures that Don Nab has posted and others about your activities. And it's always exciting to see great clubs. And this is obviously one of them. I've had a great deal of pleasure meeting a number of you. The Astronomical League is 78 years old. We now have 24,000 members, the largest we've ever been. As many of you know, we have 67 observing programs that are regular regimens of observing, some with as few as 50 objects to observe, some with as many as 2,379 to observe. And I'm into that last one in the home stretch, but it's been quite a battle. I will say that we try to do things that are supportive of clubs that make observing more interesting for people, that drive them to observe new things that they might not have otherwise observed. And these programs do that. I really got heavily involved in the observing programs during COVID and have pursued it with great vigor ever since then on every available night. So I hope you will participate in those. Just start one. They become addictive, believe me, like collecting these elements did, unfortunately for me. So the league also offers a lot of side benefits. One is the ability for you to post articles and images in the reflector. We use member-supported content for Reflector, so I hope you will consider submitting material to our editorial staff. One of our national awards each year goes to webmasters and to newsletter editors. And these are major awards that are given to people who dedicate themselves to web mastery, which of course is the main way a club communicates with the world, and newsletters, which is the way a club communicates with its own members. And that may be the more critical one. Your resource here in Tom Nolasco is absolutely fantastic. I've seen the newsletter, 30 pages. Imagine doing this if you were responsible for it. Putting in scientific content, writing original content as he does, posting images submitted by the members of the club, posting links, posting calendars and events on a regular monthly basis. It's an incredible task. And Tom won our national award this year for the newsletter award, the Mabel Stearns Newsletter Award, named after one of our older initial editors back in history. So is Tom here? Yeah. Hopefully. Yeah, this is the plaque that is given each year to the winner of the Mabel Stearns Newsletter Award. And again, the amount of work represented by this is absolutely extraordinary. So I'm just going to hold this for a picture for you.
Thank you.
And I want to thank you for having me tonight. Thank you, Jan. Appreciate it.
Well, we certainly have enjoyed your presence here. We appreciate it. And for those of you who didn't get to take a look at the display that Chuck brought with him with over 100 elements and lots of good information about them all. And it'll be up after the meeting, so you can take a look then. Okay, now to the mundane. Couple of things that are happening around the club. Just wanted to draw your attention to it. Next month, we will not be in this room. We will be at Fort Washington State Park. And we'll have our annual picnic and astronomy fair. And this year we're doing astronomy themed workshops on different topics. So you can sign up for a workshop that's on some topic that you're interested in. We'll have door prizes, we'll have free food. You can get help with your telescope, and it's open to the public. So please join us. It'll be lots of fun. This is, I think, the 4th year we've done it, and it's always a great time. Upcoming events. There's the astronomy fair you just heard about. We have solar observing happening during Community Day at Limerick Township. So anyone who wants to help with that, check out that insert on the website or the event on the website. Take a click on it and you can see where it is and maybe help out and volunteer there. September 14th will be our public star party at Valley Forge also. So you can observe the sun during the day and then you can go to Valley Forge in the evening. Then September 18th is the astrophotography workshop. And on September 21st, the Great American Camp Out at Temple Ambler. And we are looking for help with that. That's a lot of fun. It's young families are learning how to camp. Teaching the kids about camping, and then one of the activities they do is they come over and look in the telescopes, and it's a super enthusiastic crowd and lots of fun. So Barry Johnson is leading that, so you'll be able to see on the website how to let him know that you might want to help with that. And also regional star parties. We have one coming up that is a DVAA event at the Big Dipper Lodge. That's September 4th through 8th. And that is at 1 mile away from Cherry Springs State Park. So it's a nice dark sky. We don't have any spots left for the cabin, I believe. Is that true? But you can camp on the field of the lodge. And that means you can go inside and get warmed up if it's cold. You can use the kitchen, you can use the bathrooms, and you can charge your devices inside the house. So that'll be something to consider. Then also the Black Forest Star Party is coming up. If you're not already registered, then it's too late. You want to say something, Bill?
If you want to, if you're planning on camping, I'm gonna have that set up on a website soon, but you need to register if you're planning on camping. Is it? I don't know if we have enough. That's like, oh, that's slots.
Thank you, Bill. And the South Jersey Star Party is coming up, and the York County Star Party. So keep an eye on the weather for those weekends. Maybe you'd like to join up. And I have some sad news to announce. Last month, we awarded Mike Tucker with a special service award, an exceptional service award, and he has passed away. So there will be a visitation tomorrow at the Borax Givnish Funeral Home in Norristown. The visitation is 1 to 2:50, and the memorial service is 3 o'clock. So I'm sure many members will be there to remember Mike, and I hope many of you can join us. And now we have a report from the welcoming chair, Brian Lee.
I'm Brian Lee, welcoming chair. We have 7 new members this month. Tom and Sonia Skravanek, Maggie Pard, and a family of 4, Daniel, Edie, Abigail, and Alyssa Ryan. So I don't think they're here tonight, but welcome.
Thank you, Brian. And I guess we should ask, how many people are here for the first time tonight? Welcome to you. That's fantastic. Hope you join us in Fort Washington. Okay, now I'm going to turn the program over to Jeremy to introduce our featured speaker.
All right, good evening, everyone. So let's see, first a quick update on upcoming programs. So you heard a little bit about the September program, which will be at Fort Washington. In October, we're going to have Jamie Rankin from Princeton University, and she's going to give us an update on the Voyager missions and what's going on with those. And in November, we'll have a presentation on Mayan cosmology, which I think will be really cool. After that is all TBA. But, tonight, we're delighted to have Ed Sion from Villanova University. So the Villanova Astronomy Department actually has 4 eds. So if you want to get your solid education, that's where you want to go. So we heard from Ed Gein a few months back. So Ed Sion will be ed number 2 for our purposes. So Ed Sion got his start at the University of Kansas, where he did his undergraduate work, and then did his graduate work at the University of Pennsylvania down the road. And since then, he has been an institution at Villanova University, working with students for quite a few years. So Ed's expertise is in cataclysmic variable stars, so basically binary star systems, including white dwarfs that are subject to instabilities, explosions, things like that. So as many of you know, we've been following T Corona Borealis. We're expecting that to have an outburst sometime this year. I was hoping maybe it would happen tonight during the meeting. I guess we'll find out if Ed's phone starts going off in the middle of the talk. So I was hoping that would be very timely, but it seems like it hasn't gone off yet, but maybe it will very shortly. So if you would have Ed come here and tell us about his work on cataclysmic variables, focusing on T Corona Borealis and related systems. So please join me in welcoming Ed Sion.
That is. So. Here's your.
Just press down. Just press down.
Oh,
We put all I see. So there is the bottom button. Okay. And then I use this.
I use this as a element.
So I put this on.
Yeah, then you don't need this at all.
Okay.
And then down is forward.
Okay, great, thanks. Well, it certainly is a pleasure and an honor for me to be here. Oh. It's certainly a pleasure.
Yeah.
Certainly a pleasure and an honor to be here to address you and just give you it's really Daniel's talk was really a tough act to follow. I'll probably bore you to tears, but it was really an excellent talk. And I'd like to introduce my work as kind of a stellar mortician. I study stars my entire career that are the final stage in the evolution of a normal star. So they're really stellar corpses, and I've studied them when they're by themselves with no companion star, and studied them once Hubble was launched, and even before Hubble was launched, studied them with companions that are gravitationally unstable. They're losing material to the white dwarf, and that white dwarf is dead as a star, but this material that comes over is fresh hydrogen-rich fuel. And so a white dwarf can actually be reincarnated or resuscitated from its final state. So T-core Bohr is broadly speaking, it's a cataclysmic variable, but it is a subset of cataclysmics in which the number of nova explosions to qualify for this list is at least 2 nova explosions in 1 century. So that's what we call a recurrent novae. Unlike supernovae, especially the type of supernovae I'm going to be talking about, the explosion, the star survives the explosion, and it's not it's not obliterated completely like the type of supernova I'll be telling you about tonight. But I can say with some confidence that T Corona Borealis is almost certainly a progenitor of a type 1a supernova. That is to say, it's going to become a type 1 event, not like the near future, but after a while, I'll get into detail about that. It's going to, when it's a type 1a supernova, it's going to reach a brightness in terms of energy emitted of 10 billion suns. In other words, 10 billion times the luminosity of the sun. A nova, which T Corona Borealis is a recurrent nova, it will have a brightness which is approximately 10 to the 5 or 100,000 times brighter than the sun. But I'll say a lot more about that coming up. So my talk is really in 3 different parts. The first part is just to introduce you to white dwarfs, in case some of you are not familiar with that kind of a star. And then to talk about what is the central engine of a nova. What's the central engine of a recurrent nova? What's the central engine of, for example, a type 1a supernova? Why do these stars explode? White dwarfs are very explosive, but why do they explode? So I hope to convey that to you in this talk and give you a sense of what the underlying physics is without getting too technical. So let's go to the next slide. And this is just another map or finding chart. T Corona Borealis, as you can see, is very close to Epsilon Corona Borealis. Some of you have already observed it, I know, but for those of you who haven't. And then that R in the center, that's another very famous member of Corona Borealis. That's it's a carbon star. It's a really exotic giant star there, and so our Corona Borealis. Anyway, that's so it's really between Boötes, that's how I pronounce it, Boötes and Hercules, the 2 constellations. So and you see the arrow pointing to T Corona Borealis. So what are these? What are the physical and orbital properties of this incredible binary system? It's a white dwarf star and a red giant, which makes it quite different from a normal cataclysmic variable where the donor star, the companion star, is a main sequence star like the sun, except typically lower mass than the sun, about half a solar mass, half a solar radius. So this is an extraordinary system because it allows us to study the physics of accretion when the donor star of the white dwarf is a red giant. So the orbital period is 227, roughly 228 days. It has an orbital inclination of about 67 degrees. I don't include error bars here, but the error bar on that is pretty small. The sun major axis, the average separation of the two, of the red giant and the white dwarf, is only 0.54 astronomical units, about half the distance from Earth to the sun, about half that distance. So it's quite close to its recipient of transferred gas. And I also want to point out just at the very beginning that all red giants in our galaxy, whether they have a companion star or whether they're single, whether they're isolated, all red giants lose huge amounts of mass. They have stellar winds because their atmospheres are not in what we call pressure gravity balance. Hydrostatic equilibrium is what it's termed. And so because the star is so distended, it's losing material, even if the companion wasn't there. It's at a very high rate. I'd say approximately for a normal giant, about 10 to the minus 7, 10 to the minus 8 solar masses per year. Now, when it becomes a supergiant, then it has super winds. These super winds carry away as much as 10 to the minus 5 solar masses per year. So all of this points to the fact that if there's a companion star, like the white dwarf, it is really going to be, you would think, swept away by the enormous mass loss that takes place. So I'll get more into that coming up. So now we go to, so the eccentricity, it's circularized due to tidal effects. Its eccentricity is like a circle. Its magnitude and quiescence, that is between these recurrent nova explosions, is plus 9.8, but then it brightens to plus 2.0. You say, well, that's not much of a that's not much of an amplitude. But in fact, remember that the companion's a red giant, so it's very luminous. So the amplitude would actually be even larger were it a normal main sequence dwarf star. So the distance is 806 parsecs, or about 3,000 light years. And one has to take into account how far away they are, just because of this, like what in Daniel's talk, this was a Gaia parallax. Gaia has just been an absolutely revolutionary spacecraft. It's given us such precise distance information. T-Core Bohr had thermonuclear explosions that are definitely confirmed in 1846 and 2024, whenever that goes off, plans to go off. 1217, there's records in the medieval history that there was a star in the position of T-Core Bohr during the Middle Ages. And then in 1787, there's also historical information, and I think it's from the Harvard Plate Collection, that it had an outburst in 1787. So I put the asterisk there because these were found by Brad Schaefer at LSU, and they're not completely totally, but I think there's a high probability that it also had outbursts at that time. The red giant is a regular M4 luminosity class 3. Its mass is humongous. It's for a interacting system with a white dwarf. It's 1.12 solar masses. But the white dwarf is also very massive, and that's why the recurrence time is 80 years, because between the mass of the white dwarf and the rate of accretion from the donor star fixes the recurrence time. So that's how we know it has to contain a massive white dwarf, and that it will, eventually explode as a nova, and as I'll be telling you, as a supernova. So for the accretion rate onto the white dwarf, there are a number of determinations in the literature, and I'd say it's more like 1.6 times 10 to the minus 8 solar masses per year. And there are two possibilities there according to a model, two different models. But in any case, those are the vital statistics of our T-Core Bohr. Okay, so now let's go to the
Bottom button. Yeah, the bottom button.
okay, thank you. So, okay, first of all, what does T-Core Bohr look like in the ultraviolet and optical? Well, you can see here what is called it's called a symbiotic recurrent nova. Symbiotic because there's a symbiotic relationship between the white dwarf and the red giant. And you'd see that the red giant is rather cool. There it is. You see, it's the wavelength scale. This is 2000 angstroms. This is a near ultraviolet. It doesn't go much beyond that, but you can see there's a very hot something in this wavelength region, coupled with an object that's very cool. You can see how the distribution of energy falls off rapidly. Okay, so that in fact the atmospheric cutoff is right about there. So these are these are ground-based observations. This is a space observation, all right, from above the atmosphere. So these are ultraviolet and optical spectrum of this system. Let's go to that. So we don't, I try to find a slide that would kind of have an artist's depiction that's physically realistic of what this system might look like. And what I can say is that, this is an accretion disk here. This is the accretion disk. The white dwarf's at the very center. And here's the red giant. The red giant is gravitationally unstable. It mostly ejects matter through what is called the inner Lagrangian point, which is right in this region here, where it's the largest closed equipotential surface, constant gravitational potential of the system. So if an atom finds itself right there, it doesn't know what star it belongs to. Does it belong to the red giant, or does that atom belong to this object? This is an accretion disk. Now, if anyone tells you that T-Core Bohr definitely has an accretion disk is possibly misleading you. We don't know for certain that there's an accretion disk. The reason is that the red giant is losing material via its wind. Now, the wind in such a system, of course, as it flows outward, the wind is going in all directions. The wind is being emitted almost isotropically, like the solar wind. The solar wind is concentrated in the plane of the solar system mostly, but you see, is there enough specific angular momentum in this gas to form an accretion disk, angular momentum per gram? And it's not clear. But there may be an accretion disk there, there may not be. It may be what we call, instead of an accretion disk, Bondi-Hoyle accretion, in which you have, we call it the fluid rate of accretion, where you have sufficient density in the gas for a tail shock wave to form, and that material accretes via that mechanism. So there's some combination of those two. To make it even more complicated, there's a thing called wind rho-slope overflow. The wind flowing out from the giant, of course, you have the strong gravitational field of the white dwarf. The wind is more concentrated in the plane of the orbit. This is called wind rho-slope overflow. And again, there are skeptics about that, and there are also people who insist that it's true. So there's still a lot of research being done on systems like this. Let's go to the next slide. And this is typical, but these are ellipsoidal variations due to the geometry of the system. You can see here, this is just a short, almost a snapshot of what's going on. These are the magnitudes that Daniel talked about, blue and visual magnitudes of color index. And this is, these are the two filters. And then another slide shows you, yeah, this strange pre-eruption dip. From the Harvard plate collections, T. Corp did the same thing in 1846. The same kind of pre-eruption dip. We don't know what caused it. It's almost certainly dust, because a red giant wind, as it flows out from the giant, it condenses into grains of silicates, of graphite, etc. These grains are blocking light. So somehow there's dust involved in what drives this pre-eruption dip. Okay, so let's go to the next slide. Now I added to this table right here, the recurrence times. So each of these, this is the elite club of recurrent novae, the only 10 known in the galaxy, our galaxy. And the shortest orbital period one is T Pyxidus, T-Pyx we call it. It has a very short orbital period. So does IM Nor, and so does Ci Aquila. These are the only known short orbital period recurrent novae. And I'll say more about those coming up. Then we have an intermediate group in this list of 10. The intermediate orbital period is given by these other, by USCO, V2487 OF, and V394 Corona Australis. By the way, USCO is a helium transfer system. In other words, the white dwarf has a helium-rich atmosphere, and the donor star is actually transferring helium to the white dwarf. Then finally, we have then T Corp itself in terms of orbital period. It's way down the list, but there it is, and you can see there its magnitude at peak of its outburst, of its explosion, and its magnitude near 10th magnitude now, an orbital period of 228 days, two known eruptions. But as I said, Brad Schaefer has found in the Harvard plate collection two other outbursts that are almost certainly real. They're almost certainly what he says they are. Then RSO and the others you can see are have very long periods. They're very well separated. The two components are well separated. And these are the number of nova explosions, thermonuclear explosions. The thermonuclear explosions, here T-Pyx is at 7, and it goes on down the list, 12 outbursts of USCO, thermonuclear outbursts, and so on. The reason I say thermonuclear is because some cataclysmic variables, in fact, a majority of them, undergo what are called dwarf movement. These are gravitational energy releases when the accretion disk falls into the white dwarf. Some source of viscosity causes angular momentum to be lost in the disk. It drains the angular momentum, and that material falls into the white dwarf, and then with a consequent release of gravitational potential energy as radiation. So, but these are all thermonuclear outbursts. None of these are gravitational energy events. Next slide. Now, what is a white dwarf? And I know a lot of you almost certainly know about this, but basically a white dwarf is an object that is so dense, so extremely dense, that if I had a teaspoon here of white dwarf material in this room, just a teaspoon, it would weigh 5.5 tons. That's how dense it is. And so you see, and then as the mass of the white dwarf increases, look what happens. It gets smaller and smaller and smaller. That's because in order to support itself against gravitational collapse, it has to increase the pressure of what we call degenerate electrons. And I'll tell you about that in a minute too. So you can see here is a white dwarf at 1.4 solar masses. That's right at the boundary of total disruption of the white dwarf. In other words, it's kind of I'll explain, it's kind of a quantum mechanical gas. It consists of electrons that are moving very, very fast, but they can't de-excite. They can't emit a photon and slow down. They can't slow down. And so the higher the density, the faster these electrons are moving. At 1.4 solar masses, they're relativistic electrons. They're moving close to the speed of light. So that creates enormous pressure. I sometimes call that quantum mechanical pressure. And so you see at 1.4 solar masses, it's called the Chandrasekhar limit. Subramanian Chandrasekhar was an astrophysicist who studied under Sir Ralph Fowler in the UK. I believe it was Fowler. Anyway, Fowler, and he then immigrated to the United States with his wife, and they set up shop at the University of Chicago. In 1985, Chandrasekhar won the Nobel Prize in Physics. He co-shared the Nobel Prize in Physics with William Fowler at Caltech. So he, this is called the Chandrasekhar limit. He was the first to show that when a white dwarf reaches that mass, it'll undergo instantaneous collapse because gravity is so strong. Even the quantum mechanical pressure of the degenerate electrons can't stop the collapse. So I'll be talking about that quite a bit as well. And Jeremy, just remind me if I'm taking too much time. It's okay? Okay. So, all right, so let's go to the next slide. And this is just, I include this just to kind of convey and share with you the basic physics of these systems. And, yeah, thanks. So the more massive these bizarre objects are, the smaller they are. You saw that on the previous slide, right? And the electron degeneracy pressure is orders of magnitude stronger than the ideal gas pressure, like the air we're breathing or like what the sun's made of, where pressure, temperature, and density are all interlocked in the equation of state. In this kind of quantum mechanical situation, because of the Pauli exclusion principle, you can only squeeze atoms down to a certain separation before the electrons all are stripped away and form a separate gas, a weird gas that, and the reason I say weird is because unlike an ideal gas where if you heat it, it expands. In electron degenerate gas, if thermonuclear reaction taking place in electron degenerate gas, there's no expansion possible. The layer where the nuclear reactions are occurring, that layer doesn't know it's being heated. And so the temperature increases to very high values, the fusion reactions become unstable, and you get what we call a thermonuclear runaway, and that's what causes a nova. A nova is an explosion that occurs in the degenerate layer, the degenerate edge of the core of the white dwarf. So white dwarfs on average are about the size of Earth. So imagine that the radius of our planet is 4,000 miles. Imagine that's the white dwarf radius. that 4,000 miles is filled with carbon oxygen nuclei. It's carbon oxygen core or just a carbon core. And so when reactions take place, they're taking place in a partially degenerate to degenerate layer. There's no expansion to cool. And so the reactions run away and you get a massive explosion, nova explosion. So the two fundamental properties of white dwarfs that makes them so explosive are this, as I said, this kind of degenerate electron gas that depends only upon the density. And so it's insensitive to being heated. Thermonuclear energy is generated in a degenerate layer. It can't expand and cool off to quench the instability. That's one reason why they're so explosive. The other reason, even more extreme, and that is that if the white dwarf receives so much mass from its companion star that its mass builds up to try to take our limit of 1.44 solar masses for a core of carbon and oxygen, you get instantaneous collapse. Instantaneous collapse in just a few seconds. The whole thing collapses, and then the carbon oxygen core detonates, and the explosion, the resulting explosion and shock wave generated completely obliterates the star. The white dwarf is gone, and there's no neutron star, there's no black hole. It's just nothing. So that really distinguishes it from a type 2 supernova. We have these very massive main sequence stars that then lose material at a high rate, but there's always a remnant these are called core collapse supernovae, and they're very massive stars, like 10 solar masses, 15 solar masses, 20 solar masses. Those objects leave a neutron star or a black hole, but the white dwarf explosion leaves no remnant. Okay, so all right, let's go to the next slide here. And just to show you what I mean by this is a phase diagram of temperature increasing upward, and to the right is the log of the density of the material. And as Jeremy knows, we use CGS units in astrophysics, but this is kilograms per meter cubed. But anyway, you can see here that in the upper left-hand corner are very hot stars, right? You see, there it is. See, that's the equation of state for a radiation pressure. So very, very hot stars are supported against gravitational collapse by radiation pressure, where A is the radiation pressure constant, T is the temperature, and P is the pressure. And we use dynes per square centimeter for pressure. This boundary is where ideal gas pressure is the same as the radiation pressure. Our sun lies in this region here. The sun is completely made up of an ideal gas, and there's the ideal gas equation of state. Mean molecular weight, the density, Boltzmann's constant, the temperature. And these are in the outer layers where you have partial ionization zones. And as some of you may know already, these partial ionization zones are what causes Cepheids to pulsate and auroral iris stars to pulsate. But this heavy black line here, this line right here, is where electron degeneracy pressure is the same as ideal gas pressure. But then as you cross this dashed line here, you see the equation of state. Look at this. There's no temperature in this expression. There's no temperature in this expression. So the star doesn't know what's being heated in a sense. So on this side, the electrons are moving so fast, they're approaching the speed of light. This is called relativistic electron degeneracy, rho to the 4/3. The pressure for non-relativistic degeneracy is rho to the 5/3. So this is why these properties I've mentioned are why they are so explosive and so interesting. Let's go to the next slide. Now this is an ordinary cataclysmic variable. Here we see a dwarf star like the sun, even smaller than maybe typically half the radius and mass of the sun. Here's the inner Lagrangian point where gas doesn't know which star it belongs to, and the slightest impulse will send it on a trajectory, which is supersonic, to form an accretion disk. Now, all these cataclysmic variables have accretion disks, except for the magnetic ones called the polars. Their magnetic fields are so strong that a disk cannot form. But anyway, this is an artwork by Dana Barry, who was at Hubble Space Telescope for many years. Now he lives in California. but he still does space art. And I thought his depiction of the cataclysm variable was just beautiful. This is my favorite of all of his work. And this, again, I was going to leave the slide out, but given that Daniel had some pretty technical slides, I don't feel so guilty. Let me show you. Let's see. Oh, wait a minute. I'm sorry. Yeah. So this essentially, what this is, think of this as the amount of mass above the core on the vertical axis. The amount of mass above the core. So here it's 10 to the minus 5.5 solar masses or stellar masses. Here it's minus 10 to the minus 4.1 stellar masses. So those are very small amounts of mass. Now this material from the donor, whether it's a red giant or white dwarf, this material is falling into the white dwarf, whether it has a disk or not. It's falling on the white dwarf. It's starting to build up material, hydrogen-rich gas just outside the core. Think of it like this. Again, Earth 4,000-mile radius. That's the radius of the carbon-oxygen core. The layer of gas above that core is ideal gas from the donor. That ideal gas, of course, that's not as explosive. However, as that material piles up on the white dwarf, it raises the pressure and temperature at the base of that accreted layer. And so once hydrogen goes off, it goes off in an electron degenerate layer. And so just like I said, it's like a time bomb. You start to build up hydrogen, the pressure goes up, 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 and then eventually there's no thermostat to quench the nuclear reaction, the heat of nuclear reactions. And so you get because of all the stored up nuclear energy, you get a massive explosion. And this is some work I did in 1985 in the Astrophysical Journal. This is see if I get this right here. Yeah, so think of this, see this right here? Well, let's talk about a recurrent nova. So in a recurrent nova, say it had an explosion here, went into quiescence. And now it builds up material, you see, versus temperature here. And you can see that you get a thermonuclear runaway here, and the white dwarf expands to red giant dimensions. That really happens. And so it engulfs the secondary star. It engulfs the donor. In other words, the donor is moving inside the white dwarf's bloated atmosphere. Then it finally, in response to the degeneracy is lifted, it then evolves toward this direction here, over to here, and then it loses mass or has surface nuclear burning after the nova explosion. In any case, the amount of accreted hydrogen, this scale here, the amount of accreted hydrogen is now way down. So then it's reached this point here where it just starts all over again, accreting material. 80 years later, in the case of T4 Bohr, every 8 years it reaches, it covers this interval of time. So it's a nice illustration of how the evolution of an accreting white dwarf in a cataclysmic variable, how it evolves. This track, I have a stellar evolution code that I kind of inherited from my dissertation advisor at the University of Pennsylvania. Running that code, now there are even more sophisticated codes now, but running that code, you generate tracks like this, and it's just amazing. This is the first explanation of the temperature range of white dwarfs and cataclysmic variables, between 100,000 degrees and even a little cooler than 10,000 degrees. And indeed, that's what we observed when we looked at these systems with Hubble Space Telescope. Okay, so let's go now to the next slide. And this is a typical nova explosion, light curve of a typical nova explosion. You can see it has an amplitude of 9 magnitudes, a pre-maximum halt, and then a final 2 maximum rise of 2 magnitudes. And then there's an early decline here, kind of like we were talking about the dip in T4 Bohr. It's not the same thing, but I mean, and here is the early decline. Astronomers who study novae and CVs, cataclysmic variables, use a T2 and T3 measurement. How long did it take for the nova to drop by 2 magnitudes, how long did it take to drop by 3 magnitudes? Here you can see, now this region here, some of these novae have dust, and the dust has formed either from the expanding shell or from in the case of red giant, or from the red giant itself, the donor. There's a final decline, and then the post-nova, now it's going to go, depending on the mass and accretion rate of the white dwarf, it may spend 80 years like T4 Bohr. It may spend hundreds of years, thousands of years, millions of years, depending on the mass of the white dwarf and the accretion rate. That's the so-called post-nova period. Okay, so now, and this is an example of a nova shell. This is Nova Persei. I think it's Nova Persei 1919. Some of you may be able to check me on that. I think it's 1919. This is the shell of Nova Persei. The amount of material in this shell is about 10 to the minus 4 solar masses. It's not like a planetary nebula, which would be quite massive. These nova shells are essentially the mass of the accreted layer that exploded. So it's about 10 to the minus 4 solar masses. Its expansion velocity, again, depending on the mass of the white dwarf, whether it's a fast nova or slow nova or intermediate, the expansion can be from hundreds of kilometers per second to thousands of kilometers per second. So a nova shell like this with such a low mass, it's not going to live as long as a planetary nebula shell. That's Nova Persei.
Ed,
Yes.
is that an actual picture or just?
That's a photograph. Yeah, that's an image. That's an image. Yes, that's an actual, those, see the filaments and it's really amazing.
What type of light is that in?
This is an optical light, but there are observations of different filters. So I think the reddish is H alpha emission, 65, 63 angstroms. Okay. So that's a nova shell. Now, not a supernova. A supernova remnant is humongous compared to this. But let's come to that. So now we go to next slide. And so look, type 1a supernovae are what are known as white dwarf supernovae, or as standard candles. They tell us not only that there has to be dark energy in the universe to prepare, because the expansion of the universe is accelerating. It's actually getting faster. And in other words, in the past, the universe was expanding more slowly, and now it's expanding faster. Well, this is a type of supernova, type 1As, a white dwarf supernova that tell us that. And so far, it has not been refuted. But even discoveries like this of type 1A supernovae are open to question. And the scientific, thank goodness, the scientific community has peer review. And peer review, you try to falsify some discovery. This is a huge discovery. It had to be, everybody tries to falsify it. What we are seeing here is the light curve. This is the blue magnitude, the light curve of a type 1, of 38 type 1A supernovae. Look how much they correspond with each other. Look how close the observations are to a theoretical light curve. This is a theoretical light curve. Look at this. That's why they're standard candles, because you know they're bright, their intrinsic brightness, and therefore you know their distance, because you know how much energy is released and so on. So this is exactly how it was done, and this led to the Nobel Prize co-shared by two groups. One group at Cal Berkeley, and the other group at Johns Hopkins, and also in Australia. And they co-shared the Nobel Prize. Saul Perlmutter and Brian Schmidt and
Adam Rees.
Thanks. Yeah. And so but look at that. Yeah, talk about standard candle. We know the apparent brightness. We know the absolute brightness, and therefore we've got the distance. And then, okay, so let's go to the next slide. So now this is the supernova part of the talk. And let me, so at present, and again, this is highly controversial, and there's no definitive work yet that you can say is completely correct. But there are two channels that we believe lead to type 1A supernovae. And that is a channel with two white dwarfs that are orbiting each other, very close orbit. gravitational radiation is dissipating angular momentum from the system, and they gradually spiral into each other and merge with the combined mass of these two white dwarfs, reaching the Chandrasekhar limit. And so you'll get a type 1A explosion now. This is called the double white dwarf channel. The other channel is called the single degenerate channel. This channel is what T-core Bohr represents. T-core Bohr and all of the current novae have been found to gain more mass from accretion than they lose by explosions. The explosions carry away less mass than they accrete. So the white dwarf grows in mass. The white dwarf actually grows in mass. And the current novae are that subset in which their white dwarfs are increasing their mass. And you saw that the white dwarf in T-core Bohr has a mass of 1.37 solar masses at present. Now, that's not the only mass energy. There's some that are 1.2, some that are 1.36, and so on. But what I have on the slide is 1.37 solar masses. T-core Bohr's white dwarf only needs to gain 0.07 solar masses before it would instantaneously collapse into a type 1A explosion. So, but then you say, well, when will that happen? We don't have a thing to worry about. It won't happen for a few million years because the accretion, the sun's so massive, and the accretion rate is very high. Anyway, that's so the single degenerate channel, that's the channel that in my work that I've worked on with that. And but there are other proponents of the double degenerate channel that still insist that their channel may be the dominant one. We'll have to wait and see. Okay, let's go to the next one. Oh, this is a supernova remnant. Now this is very massive. This is a type 2 supernova remnant. I think this is the Crab Nebula. I think it's the Crab Nebula. And let's see here. So just quickly, white dwarf supernova are the biggest thermonuclear explosions in the universe. You have a release of energy 20 billion megatons of TNT. In other words, if there were a thermonuclear exchange between Russia and the United States, this is a tiny fraction of that megatonnage. Billion megatons of TNT. This peak luminosity rivals that of a large galaxy. The best example is this system here. Oops, sorry. Sorry about that. The best example, look how bright the type 1A explosion, how bright the type 1A supernova is to its parent galaxy. We know it's a member of this galaxy, and it went off as a type 1A supernova. We also see up here another one. Look how bright it is compared to the galaxy itself. And here as well, you see. So these are very luminous. That's why they're so important in terms of cosmology, in measuring stellar distances. How big is the universe? And they also produce lots of the iron group elements, including, and you may be skeptical of this, and some are, some are not, but the blood, human blood, our blood, was made in a type 1A supernova. They're the major contributor of iron in our solar system. So anything that's iron, like in human blood, came from a type 1A supernova originally. Let's go to the next slide. So again, this is a kind of a snapshot of what happens in a type 1A supernova explosion. Remember, you're talking about carbon core or carbon oxygen core, and when that core reaches the Chandrasekhar limit, 1.44 solar masses, it undergoes instantaneous collapse, raising the core temperature to 700 billion degrees. It starts as a nuclear flame deep inside the core, and then eventually that flame turns into a complete nuclear burning of the entire carbon core. The carbon is then almost instantaneously converted to neon, magnesium, sodium. Oh, sorry, did it again. And then oxygen is converted, the oxygen part of the core is converted to sulfur, silicon is converted to nickel, 40%, 60% of the core, is converted to nickel. The nickel immediately decays into cobalt and iron. The iron nuclei absorb photons because there's photodisintegration going on. They absorb photons, and the iron, the increased radiation, the intensity, then photodissociates helium nuclei or alpha particles. The overlying layers of the core, it has no pressure support now. And so, wham, it falls very, very fast into the deeper part of the core. The alpha particles photodissociate into electrons, protons, and neutrons. The electrons are crushed into protons, forming a neutron star at the center of this type 1A. A neutron star forms, but even nuclear degeneracy, the pressure of degenerate nuclei of atoms, is not strong enough to stop it from collapsing more. The neutron star is crushed, if you can imagine. It's crushed. The outer layers of the white dwarf bounce off the neutron degenerate core, sending a shock wave outward. The enormous explosive energy during the collapse and rebound cannot be contained. The white dwarf explodes, leaving no remnant, neither a neutron star nor a black hole. Very strange. The light curve of a type 1A supernova is governed by these two reactions. These are radioactive nuclei, nickel decaying into cobalt plus a positron plus an electron neutrino plus a gamma ray with a half-life of only 6.1 days. Then cobalt 56 decays into iron 56 plus a positron plus an electron neutrino plus a gamma ray. So these are what really powers the light curve, okay, and governs or dominates the evolution of the light curve following the explosion, are these radioisotopes. And so a type 1A supernova provides a rich supply of iron group elements. So T-core bohr is going to do this, such as chromium, manganese, iron, cobalt, and nickel. They produce 1/2 to 2/3 of these key elements in our galaxy, even though they are 3 to 6 times more rare than the massive core collapse supernovae. The core collapse supernovae happen more often, but in this case, the white dwarf supernovae, they have a disproportionate effect on the abundance of iron and other heavy elements in our part of the galaxy and also in its solar neighborhood. The type 1A events also forge intermediate mass elements, including manganese, aluminum, silicon, sulfur, and calcium. So T-core bohr, we can say with some confidence, will probably be doing this, you see? And it's only 2,000 light years away, and it's been extensively studied with Hubble, and also a previous ultraviolet satellite that had a unexpectedly long lifetime, the International Robotic Explorer. T-core bohr was also intensively studied by the IUE spacecraft, and then followed up with the Hubble. I got my first Hubble time the year it was launched, and that was 91. And so it was an incredible thing that now one could study cataclysmic variables with this very powerful 90-inch aperture spacecraft that it's just been amazing. And so I guess, shall I think this is it. I think this is. Oh yeah, okay. Oh, I just wrote a book on accretive white dwarfs, but don't buy it. It's very expensive. It was listed first by, it's a UK publisher, it was listed first as $190. Now it's down to 119. So if you wait long enough, maybe it'll be a more reasonable amount. But anyway, that's the, it's not going to be in the New York Times bestseller. So, but I was called by a New York Times reporter today, so who knows? Maybe it'll promote the. Anyway, and that's the cover of the book. So I'm happy to take any questions you guys have, and thank you very much for inviting me to be here.
So we'll try to get the
Oh yeah.
questions on the mic so that we can move them from.
So you talk about standard candles.
how standard are they? I mean, I saw the chart, but I mean, obviously it varies 1%, 2%. And you know, at various places, how standard is the standard?
In the case of type 1A supernovae.
Yeah, I shut it off.
In the case of type 1A supernovae, I'd have to say, really honestly, that it's quasi-standard candle. It's quasi.
Yeah.
Yeah.
That's what the chart looked like. I
Yeah,
just
yeah,
couldn't
yeah.
figure out the number.
I mean,
Exactly.
between an accelerating universe, a static universe, and a collapsing universe, the differences between those three things.
Well, the reason why it's interesting, right, is effective standard candles we use for measuring distance, and
Exactly.
if they're not as standard as they may, are we off by 1% sometimes, or
Yeah.
3, or you know,
That's an ongoing.
the ladder, how it goes.
Ongoing
Right?
research as we
Yeah.
speak. And that's
Okay.
exactly what, there's still a little bit of jitteriness about standard candle for the type 1As. There are variants of type 1As
Yeah.
that don't match, what I showed you on that diagram were all the standard type 1As. But you also have variations in that. And also there's now a new model for a type 1A of double detonation model. Where the helium layer builds up, becomes unstable, blows up, and then ignites the carbon oxygen core. So that's a totally different channel.
Got it.
I didn't show you that channel, but. Yeah.
And is there any way to determine from a recurrent nova event whether that recurrent nova is an imminent 1A?
I looked at that for the sake of this report over the New York Times, and all the white dwarf needs, you're talking about T-core hole. Yeah. All it needs is 0.07 solar masses. But if you calculate the time that it would take to reach from 1.37 to 1.44, it's a long time. And besides that, it's far away, we're not in any danger.
You mentioned about a previous explosion on the Harvard plates.
Yes.
But you said it was 1787, so there was no photography back then.
The Harvard plate collection,
Yeah.
no, it has visual, I think it has visual measurements.
All right, so it's not in the plate collection, it's been visually.
Yes, I stand corrected. Yeah, it's very old, but not that old.
Right. And then my second question was, you mentioned about during the time that the electron degeneracy pressure that the star can radiate any heat from the thermonuclear explosion. Then how does the star radiate at all?
Because when the explosion occurs, it lifts the degeneracy. And so these degenerate electrons, they can't lose energy because all the lower lying energy states are filled by the Pauli exclusion principle. So there's a tremendous
But even when there's no explosion,
right.
just a quiet, isolated white dwarf with full electron degeneracy, how does it radiate them?
Oh, it radiates by a layer above the core, which is about the same dimensions as our upper atmosphere. From the surface of Earth. Yeah, yeah, from the surface of Earth up to say 500 kilometers roughly. The white dwarf, all white dwarfs have this non-degenerate gas layer, which is a tiny fraction of the radius of the white dwarf, but it's an ideal gas.
Okay, excellent. Thank you.
You're welcome.
Ed, you were talking about the accretion disk.
Right.
On the white dwarf.
Yes.
So does that mean that if there is an accretion disk, that some of the mass that gets applied to the white dwarf does not get evenly distributed?
Yes.
Distributed, like it's more likely to be on the equatorial plane or the plane of the accretion disk?
That's right. That the accretion disk will be largely in the plane of the orbit of the two stars. The only exception is if it's a magnetic white dwarf. A magnetic white dwarf you can have mega Gauss strong fields. Then an accretion disk doesn't form, but matter still gets in by accreting at the magnetic poles, assuming it's a dipole field. You see, bonded foil body oil, we don't really know how efficient it is. There are numerical simulations done at several places around the world. There are three-dimensional hydrodynamic simulations. What I showed you on that evolution of a cataclysmic variable white dwarf was a quasi-static. You can only go down to time steps of a minute, maybe 40 seconds, 50 seconds, and then your computer code stops because of numerical instabilities. With a hydrodynamic code, you go down to time steps of microseconds. You know, it's incredible, but it takes a lot of computer time. But such simulations are down the road. They're going to occur. Did I answer your? Yeah. Oh, there it is. Yeah, it's simulations are, you know, plus artificial intelligence are the future of astrophysics, and yeah, so the time steps. I mean, inside of a star, the physical information is communicated by small amplitude sound waves, by small amplitude waves. So if your time step is larger than that time scale for an atom to cross one zone, you have a star divided into zones, then it will violate the Coulomb condition, which says that, you know, physical information is only transmitted with the speed of a low amplitude wave. So these supercomputers, as they evolve, they're going to get down to even smaller time steps. If the time step's too large, you lose information. There could be instabilities you'll miss.
Okay, any more questions?
Good.
Thank you so much.
Thank you.
Thanks very much, and thanks, Chuck, for making the trip to visit us. And I encourage everyone.
AL members.
Of course, we are AL members. Yes. And please take some time before you leave to check out a collection back there of interesting elements. 100 elements in the flesh.
From supernovas.
So to speak, yes, from supernovas. Bye, everyone, and we'll see you next month at Fort Washington. Well, thanks, Jeremy,
Thank you.
for fielding that last night, or that last minute collapse.
Things was here. Elements in graded. Elements. Later, those elements.
Daniel sure is a poised sophomore, isn't he?